Welcome to the next video in the binary series. In this video, we are going to talk about the floating point notation again, but in this video now, we're going to use the excess notation for the power. So first of all, we're going to recap what excess notation is. Then we're going to go into details about the floating point notation. Then I'm gonna show you how you can normalize the mantissa. And then I'm going to show you examples of how to convert decimal numbers to floating point notation and the other way around. And at the end, as always, you will get a chance to do some practice questions yourself, which all have the answers. So, excess notation. The important things to know about excess notation is that it is always fixed bit length. Depending on how many bits your excess notation is, 0 will always be represented by 1 and the rest of the digits followed by with 0. So for example, in 3 bits excess notation, 1, 0, 0 will be the equivalent of 0 in decimal. In 5 bits excess notation, you would have 1 and 4 zeros to be equal to the decimal 0. Now, one thing that you need to notice now is that 0 become a signed number. And on top of that, all of the positive numbers are now going to be starting with 1, and all of the negative numbers are going to start with 0. Opposite of what we learned in the 2's complement notation. If you need more details on the excess notation, go and have a look at the video which is dedicated to the excess notation. Before we go into the practical calculations, what I'd like to talk about a little bit is vocabulary. When we write a number in the a times 10 to the power of n format, there are two important concepts that we need to know here. A in this format is called the mantissa, and n in this format called the exponent. So the mantissa is always the number multiplied by a power of 10, and the exponent is that power. So for example, I can talk about 3.1 times 10 to the 5. In this case, the mantissa is the 3.1 and the exponent is the 5. Now, why do we need to talk about these two components? It's simply because the floating point notation is based around a power format, but because the floating point notation is base 2, the difference there will be that this 10 will become a 2. But we still have got the concept of mantissa and exponent. For example, in binary, you probably would have 4.5 in decimal, obviously, times 2 to the power of 3. In that case, the 4.5 would be your mantissa and 3 would be your exponent. But the base now, because we're in binary, would be the 2. One more thing that you will hear me talking about is the so-called truncation error. And the truncation error occurs when we need to cut the digit short. So for example, floating point notation has got fixed bits. So if our bits are shorter in the notation than the actual number we're trying to represent, then we're gonna come across something called the truncation error. That's basically if you have got a 6 bits long number but you only have got 4 bits to represent it, the last 2 bits would be lost throughout the conversion, and that would be the truncation error. Now let's get down to the floating point notation. You probably have seen this sequence before. What this sequence means, in this case the S is your sign bit, and this sign bit is 1 for negative numbers and 0 for positive numbers. Okay, in this case, the negative and positive refers to the overall decimal number that you're trying to convert into floating point notation, being positive or negative. For the duration of this video, I'm only going to talk about the 8 bits floating point notation, which is very simple and straightforward to understand the logic behind it, but obviously 8 bits is really short, so we can't really express a lot of numbers. So in reality, the computer is using longer sequence to represent these numbers. The next section of this sequence is the E1, E2, E3, which is basically the exponent expressed in a 3 bits excess notation. Okay, so if you have watched the previous video on floating point, the difference here is now that the exponent is in excess notation, while in the previous video we used the 2's complement notation. And the last part of the sequence is the mantissa, but we're only using 4 bits for the mantissa. So before we can start to do the conversions, one thing I'd like to make sure that you understand is how the normalization of the mantissa process is going. So, for example, you have already converted your binary number and you end up with this number, 0.0011001. How would you normalize it? Now, the normalized mantissa which you're going to have to use in the 8 bits floating point notation for the last 4 bits, is always starting with a 0 radix point 1 format. So what we need to do in here is from this, we need to convert the number into this format. So then the normalized mantissa would be just the number starting from here. So that is 0 radix point 11001. Now, what we can see here is that I have got 1, 2, 3, 4, 5 bits behind the point. So that extra bit I cannot represent in the 8 bits floating point notation. So that bit is the so-called truncation error that I have mentioned a few minutes ago. So this would be the normalized mantissa, but what would be the exponent? Well, the exponent is always from the computer's point of view. So, what do I have to tell the computer to convert back this normalized mantissa into the original number? So, I would have to tell the computer to move the radix point, remember it's here now, 2 places to the negative direction. So, the exponent would be -2. Second example, 101, radix point 10010. Again, how do we do the normalization? Again, it has to be 0 radix point 1. And if I look at this number, that means I would need to move the point here. So I need to copy the sequence from then on, and that's basically 1, 0, 1, 1, 0, 0, 1. The last 0 I don't need to write out because there's no other digits following it. But again, I only got 4 bits for the mantissa, so these 3 digits are again truncation error. So the normalized mantissa therefore will be 0 radix point 1011. And the exponent, again, what's the exponent? What do I have to tell the computer? How many places from the normalized would the computer have to move to go back to the original? So the computer now have to move from here to here, which is the original place. So that would be +3. Next normalization example, 0 radix point, 3 zeros, 1 0 1. So the normalized mantissa now will be 0.1 0 0 1. In this specific case, I have enough space, so there is no truncation error, but I still need to find the exponent. So the exponent, remember, this is what the computer is given. You need to tell the computer to go back to the original number. So how would the computer go back from this to the original number? So it was here. It needs to go 3 places to the negative direction, so that will be -3. And the last example, okay, again, how do we do the normalization process? Again, the normalized mantissa have to start with 0.1 and followed with the rest of the digits. So in this case, after the first 1, I have got 2 zeros, 2 ones, 2 zeros, and a 1. Again, that 0 is unnecessary because there is no other digits following it. So the normalized mantissa, therefore, will be the first 4 digits behind the radix point. So again, I have got quite a big truncation error. And the exponent. So this is what the computer is given. What do we need to tell the computer to come back to the original number? Well, the computer have to move the point, the radix point, 1, 2, 3, 4 places to get back to the original one. So the exponent in this case would be +4. Now, I hope that this clears out how to do the normalization and the important part of the exponent. But let's have a look at now some of the floating point notation examples. Before we go into that though, what I want to give you is a set of instructions on how to do the floating point notation in a step-by-step format. So first and easiest part will be to identify the sign bit. Well, if you have got a positive decimal number that you need to convert, you're going to record the first digit to be 0, and if you have a negative number, negative decimal number, then your first digit in the floating point notation will be 1 to indicate that it's a negative number. Then you're going to have to convert your decimal number into binary. Once the conversion is done, you will need to find the normalized mantissa. So what you will need to do is to move the radix point to the 0.1 format and record the first 4 digits after the point, and that is the normalized mantissa that goes into the floating point notation. The 0 point in the front doesn't become part of the floating point notation because it's told to the computer that that is how it starts. So it's not an information that you need to give the computer as an extra information. Then you also have to find the exponent and express that exponent in the 3 bits excess notation. Important here again is to put yourself into the computer's position. So what would you have to tell the computer to get back from the normalized mantissa to the original number? And finally, you just have to pick all these small information together and record them in the sequence of sign, exponents, and mantissa. It probably takes quite a bit to explain it, but when you will see that when you're looking at examples, they're slightly more easy to follow. So the first example, I have got -1 and a quarter. So the sign bit therefore will be 1 because I have got a negative number. The next thing I need to do is convert this decimal number into binary. So what I need to do, I need to build up the conversion place values. So 1, 2, 4, radix point, half, a quarter, and an 8. There is a video that's showing you how to convert fractions into binary numbers, so if you have forgotten about it, do check out that video. 1, so I need a 1 digit here, and a quarter, so I need a 0 in here. So my original number, the 1 and a quarter, is equal to 1 radix point 01. Now I need to normalize it. The normalization process, remember, is 0.1. So the sequence after it is 0, 1, and because I need 4 bits, I need to fit a 0 here. And this part will be the bits that I'm going to record in the floating point notation. Now I have to find the exponent. This is the number that is the computer given. What do the computer have to do to go back to the original number? It has to move the radix point 1 into the positive direction. So the exponent is positive 1. But this is the decimal format. So what is positive 1 looks like in 3 bits excess notation. So the 3 bits excess notation you can always build up by remembering this sequence. 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. The 1 followed with 0, that is equal to 0, and positive 1 is above it. So 1, 0, 1 is equivalent to positive 1 in the excess notation. So the exponent is 1, 0, 1, and the normalized mantissa is 1, 0, 1, 0. So negative 1 and a quarter is equal to 1, 1, 0, 1, 1, 0, 1, 0 in 8 bits floating point notation. Sign, exponent, normalized mantissa. Let's look at the second example. Minus 2 and 3/8. The sign bit always going to be easy. It's a negative number again, so the sign bit going to be 1. Now let's look at and convert the number. So 2 and 3/8, again build up the binary place values. 1, 2, I'm not going to need anything more because 2 is the biggest number that I use there. And then I have got a half, a quarter, and an 8. Now what's going on in here? I've got 2. I don't have any 1, so I put a 0 there. And out of the fractions, I've got 3/8. But I can't put 3 in here because I've only got digits 1 and 0 to use. So I can only put 1 into here. Now, if I've got the 3/8, if I used 1/8 out from there, I still left with 2/8. But 2/8 conveniently cancels down to a quarter. So 3/8 is the sum of a quarter and an 8. So I need to put a 0 to the half because I have not used it. So that is the binary equivalent of my decimal number. So what I need to do now, I need to normalize the mantissa. So it's going to be the 0.1, and then what else do I have there? 0, 0, 1, 1. Now I ended up with 5 digits here, so I have to cut it down to 4 digits, which means I'm going to have a truncation error. So the mantissa is 1, 0, 0, 1. What is the exponent? This is the number that the computer is given, and the computer needs to turn it back to the original number. So what does the computer have to do with the radix point? Move it 2 places to the positive direction. So the exponent will be positive 2. And now, because we built up the excess notation table in the previous page, we can just turn back. So positive 2 is here. So the exponent will be 1, 1, 0 in the excess notation. So the exponent is 110. And now we can build up the floating point notation. So the minus 2 3/8 is equal to 1, followed with the exponent 110, and followed with the mantissa. Now, because we had the truncation error, if I was to convert this floating point notation back into decimal, I will not have the exact minus 2 3/8 because I'm missing one digit. So this is already showing you the limitations of the 8 bits floating point notation. This is a very small notation, so small numbers like minus 2 3/8 cannot be represented exactly. So the computer uses therefore a lot bigger notation. Let's look at the next example. 3 3/4. So the sign bit now is 0 because this is a positive decimal number. Remember, if there is no sign in front of a decimal number, that always means positive. Next thing I need to do is build up the binary equivalent of this decimal fraction. So 1, 2, radix point, half, a quarter, and an 8. 3 is the sum of 2 and 1, and 3/4 is the sum of half and a quarter. So what I need to do now, I need to find the normalized mantissa. 0, radix point 1, and that's quite easy because I just have to follow it through and put the 4 ones together. The next step is to find the exponent. And again, the exponent, what do I need to tell the computer to do to move back to the original number? So to move back to the original number, the computer again have to move 2 places to the positive direction. Now that's handy because we already found positive 2 in the excess notation, as we had to use the same thing for the previous example, and that is 110. So the mantissa will be these 4 bits, and the exponent is these 3 bits. So pull the whole thing together. So 3 3/4 then will be equal to 0, followed by the exponent 110, and followed by the mantissa 1111. And the last example, 2 5/8. The sign bit again going to be 0 because this is again a positive decimal number. Converting it into binary, we will need 2, 1, radix point, a half, a quarter, and an 8. 2 is 1, 0, and in the radix point. This is similar to a previous example because again I have got 5/8, but I can't put 5 in here because I've only got 1s and 0s. So I can only choose 1/8. And how many more do I have left if I take that 1/8 out? Well, that's 4/8. But 4/8 conveniently cancels down to a half. Every fraction where the numerator is the half of the denominator, or when the denominator is double of the numerator, that is always equivalent to a half. So 5/8 is the sum of an 8 and a half. So I have to use a half, and I'm not using any of the quarters. So now I need to normalize this number to find the normalized mantissa. So again, it's gonna end up in the 0 radix point 1 format, and what follows there? 0, 1, 0, 1. Again, what I see here is that I have ended up with 5 digits, so only the first 4 is the one that's going to be part of my number. So that's going to be my mantissa. And again, I need to identify the exponent. and the exponent is, again, how many places do I need to move the radix point to get back to the original number? And again, that is positive 2, which is 1, 1, 0, just as in the previous two examples. So pull it all together. 2 and 5 over 8 is 8 bits floating point notation is 0, followed by the exponent and followed by the mantissa. And again, just as in one of the previous examples, because I have got this truncation error, when I convert this floating point back into decimal, I will not get the exact 2 and 5/8. I hope that you now understand how to convert decimal numbers into floating point notation, but we also need to look at how to convert floating point notation back into decimal numbers. So what you need to do first then is to remember that the floating point notation is a sequence that builds up in 3 different groups. So when you look at that group, you need to break it up according to the sign, the exponent and the mantissa. Again, the easiest part will be to identify the sign. Remember, if the sign is 0, you've got positive number, and if the sign is 1, you've got a negative number. Then what you want to do is to pick up the exponent and decode it back into decimal, knowing that this is in excess notation. And once you know the exponent, then you look at your normalized mantissa and you move the radix point according to the exponent. Now you renormalized the mantissa. This is now the original number in binary form, and the last step will be to convert it back into decimal. So let's have a look at a few examples. So here is the first number, 0, 1, 0, 1, 1, 0, 0, 1. So the sign bit is 0, so I know I've got a positive number. The exponent is 1, 0, 1. We're going to have a look at in a minute what that is. And the mantissa is 1, 0, 0, 1. But don't forget that it always starts with a 0 point, which we don't tell the computer because that is the case for every single one of the numbers. So let's have a look at what this 101 is in 2 bits excess. In the 2 bits excess, 101 is positive 1. That means that I need to look at the mantissa and move the radix point 1 in the positive direction. So the new radix point will have to go here. So the original number is 1 radix point 0, 0, 1. Now what I need to do is to convert it back to decimal. So the radix point is here. This is the place value of 1. That's a place value of half. That's a place value of quarter. And that's a place value of 8. So this 8 bits floating point notation is 1 and 1/8. Don't forget, it starts with a 0, it's a positive number, so we don't have to write any sign in front. Next example, 1, 0, 1, 0, 1, 1, 0, 1. So again, the sign bit is 1, which means that I have got a negative number. The exponent is 0, 1, 0, which we're going to have a look at in a minute, what that is in excess. And the normalized mantissa is 1, 1, 0, 1. Don't forget that there is a 0 and the radix point in front. So what is the exponent? The exponent 0, 1, 0 is negative 2. So this is the mantissa that the computer was given. So come back to the original number. I need to move the radix point from here 2 places to the negative direction. one place, two places. So that will be 0 radix point followed by with 2 zeros, 1 1 0 1. So now comes the place values. 1 radix point, a half, a quarter, an 8, a 16th, a 32th, and a 64th. Now I just need to add together the place values that have got 1 under them. So that will be an 8 plus a 16th plus a 1 over 64. Now, when adding fractions together, you need to bring them to the common denominator. The common denominator will be always the biggest number. And what you're going to do, you're just going to think about how many times do you need to double each of them to get to 64. So if I double 16, that would be 32. If I would double that again, that would be 64. So if I double it twice, that's the same as multiplying by 4. So 1/6 is 4 over 64. The 1 over 64 won't change. And the 8. Double the 8 gives you 16. Double the 8 again gives you 32. And double it again gives you 64. So you doubled it 3 times, which means that you multiplied it by 8. So 1/8 is 8 over 64. Another way of thinking about it is how many times 16 goes into 64, which is 4, and how many times 8 goes into 64, which is 8 again. And now you can just add them together by not changing the denominator and adding the numerators together. So 8 plus 4 gives you 12, plus 1 gives you 13. So this floating point notation number is a negative 13 over 64. The next example is 1 0 1 1 1 1 0 0. So the sign bit is 1, which tells me that I'm working with a negative number. The exponent is 0 1 1, which we're going to find out in a minute what that is, and the mantissa is 1 1 0 0 with the 0 point in front. So let's check on the exponent. 0 1 1 is negative 1 again. So when I look at this number, in this case I only need to move it 1 places to the negative direction. So the original number is 0 radix point 0 1 1. Now those 2 zeros I don't have to write down because they're not going to be part of the calculation anyway. So the place value is 1 radix point, a half, a quarter, and an 8. So what I need to do now, I need to add together a quarter and an 8. Now a quarter is 2 eighths. So altogether I've got 3 eighths. So it's a nice and simple number. Remember it was negative 3 eighths. And then let's look at the last example. 0 1 1 0 1 1 0 0. So the sign is 0. That tells me I'm working with a positive number. The exponent is 1 1 0. We're going to have a look at in a minute what that is in excess notation. And the mantissa is 1 1 0 0, not forgetting that I need a 0 point in front. So what is 1 1 0 in excess? 1 1 0 is positive 2. So the exponent is positive 2, which means I need to move this radix point 2 places in a positive direction. So in this case I'm moving here. So the number will be 1 1 radix point 0 0, but that's quite simple because if there are no zeros, those place values I don't have to take into account, which then means that this is just a nice and simple positive 3. So I hope that you understand a little bit better now how the 8 bits floating point notation works when you need to use excess notation for the exponent. In the next slide, I'm going to give you a few practice questions that you can try on your own, and then you will find the answers to them. Here are the questions. And here are the answers.